Let's do the one-way between ANOVA analysis. When do we use the one-way between ANOVA? We have one independent variable, it's categorical, three or more conditions or levels, and it's a between design with one continuous dependent variable. What is the goal? To test if there is a difference among the three or more means. The data entry is identical to the independent samples t-test. You have a participant column, a participant variable, that's ID type. You have an independent variable column, that's nominal, which is categorical and tells you who belongs to which condition. Remember, participants only belong to one condition. There's condition A, B, and C in this example. And the dependent variable is continuous. I'm going to be silent, but this will show you the buttons you press to get all the results and analyses you need. And one final time. So the first thing we're going to look at is the pattern. In order to do that, I like to look at Jamovi's graphs. We can see here that condition A is less than condition B, which is also less than condition C. That is a pattern that we are seeing. Now, what does this mean? That depends on your example. These examples do not have context, so you will have to figure out what this means for your problem. In terms of my p-value, which is next, I look at this part of the output, and I specifically look at the p-value. Is that less than 0.05? This is significant. Now, that means there's some difference among the three means, but it doesn't pinpoint where those differences are. Now, the effect size for an ANOVA is called eta squared, and it has an identical interpretation to r squared. Eta squared times 100 equals percent. So in this case, my eta squared is 0.88 times 100 is 88%. What does that mean? If this were a true experiment, it means my IV causes 88% of the DV. In a correlation study where you have a categorical IV like identity that's not randomly assigned, you would say my IV is associated with 88% of the DV. Now, this also has small, medium, and large values. An eta squared of 0.01 or 1% is small, 0.05 or 5% is medium, 0.16 or 16% is large. Unfortunately, Jamovi does not provide a confidence interval for this statistic. So all you can say is that in your data, the effect appears to be large. With this test, with the ANOVA, we call it an omnibus test. It just tells us if there's some difference among the three means. It doesn't pinpoint it. To pinpoint the difference, we have to run post hoc tests. Each of these tests that compares each of these two means has its own pattern, p-value, and population effect size. So in this example, we're comparing condition A to condition B. That has its own pattern, p-value, and population effect size. The population effect size for these postdocs is, again, Cohen's d, and it will give you the 95% CI of Cohen's d. Then we got to compare A to C and B to C. So we have three comparisons, each with their own pattern, p-value, and effect size. So with the postdoc tests, we get a lot of different patterns. Let's examine the first one. We see that condition A is less than condition B. We got to know, is this significant now? We have to look at this part of the output right here, look at condition A versus condition B, and find its p-value. That is a significant difference because it's less than 0.05. Right next to it, we get the Cohen's d's. We see the Cohen's d in the sample is negative 3.21. That's large. That's larger than negative 0.8. And the 95% confidence interval ranges from negative large to negative large. So we know this effect is not only significant, it's a large effect where condition A is less than condition B. The second comparison we want to make is between condition A and condition C. That is this line right here. I know that condition A is missing, but that's because Jamovi just carries it down and finds it redundant to write it again. So this line compares condition A from condition C. C appears to be larger than A. Is that significant? Yes, it is, less than 0.05. And then we look at our sample effect size and our 95 CI of effect size to get our population effect size. We know that the sample effect size is large and the population, negative large, and the population effect size is between negative large and negative large because those are both greater than negative 0.8. And then finally, we want to compare, is condition B different than condition C? It looks like condition B is less than condition C. Is this significant? Yes, it is. We look at our effect size. What do we know? The sample effect size is negative 2.81, and the population effect size is between negative 4.67 and negative 0.95. All of those are negative large. The population effect size is negative large.